Hello, this week we will do some thermochemistry experiments. In addition to this presentation, before coming to the lab, you must also read the introduction to the lab in the course pack and review chapter 5 on calorimetry. What's the point of this lab? In this lab, we will try to get experience with calorimetry. We measure the heat flows from the temperature changes. We practice calorimetry calculations, evaluate the heat loss and heat gained, and we perform a combustion reaction to determine which fuel produces the most heat per gram. Here we have a setup. We will burn some fuel and calculate the change in the temperature of the water on the top. And based on the change in the temperature, we use the calorimetry equation to calculate what is the heat of combustion for the fuel. First, let's review some basic concepts. Heat is denoted as Q, which is an energy transfer between system and the surroundings due to the temperature difference. When surroundings are hotter than the system, the heat flows from the surroundings to the system. We call this an endothermic process. When the surroundings are cooler than the system, the heat flows from the system to the surroundings. We call this is exothermic process. So heat flows from the hot to the cold object. But heat flow cannot be measured directly. Instead, the effects of heat flow are measured. We relate the temperature changes and heat flow via a specific heat capacity C, which has formula Q equal to mc delta T, where C is a specific heat capacity of an object which has a unit of joule per gram Celsius. And to differentiate between the specific heat capacity and the heat capacity, we will use Cs for the specific heat capacity and C for the heat capacity. And Q is heat gain or loss by the object, and M is the mass of the object. T is the temperature change in Celsius of an object due to the heat flow. Heat capacity, Cs, often just called as specific heat, defined as the Q divided by M delta T as from the previous equation. And specific heat can be determined if Q, M, and delta T are known for an object changing temperature in contact with surroundings at a different temperature. We can measure the mass and the change in identity very easily. Therefore, we will find the Q by calorimetry. Energy is conserved, so when heat flows to or from a system, it must be equal in magnitude but opposite in size to the heat flowing from or to the surroundings. Therefore, Q of system always have an opposite side with the Q of the surrounding. In a calorimeter, we measure the Q of the surrounding, which equal to the mass of surrounding multiplied with the specific heat capacity of the surrounding multiplied with the change in temperature of the surrounding. This requires that we know the specific heat of the surrounding, which usually is water, and the value is 4.184 joule per gram per Celsius. In an isolated chamber, at the initial conditions, we know the temperature, the mass, and the specific heat of the surrounding, and the mass of the system. After the heat exchange and we reach to the equilibrium, we have the temperature of the surrounding equals to the temperature of the system. We will use the change in the temperature of the surrounding to find out the Q of the surroundings. And the heat that flows to from the surroundings is quantified by the equation Q of surrounding equal to mass times specific heat times the change in temperature. Everything on the right side is known, and the change in the delta T is calculated from the measure of temperatures. And the specific heat of water is a constant, and the mass of the water is measured initially. Next, after we calculate the heat of the surroundings, we use a lot of the energy conservation to find the Q of the system, and the negative side is super important. In our experiment, we will assemble a can of water, which is the surroundings, and we need to measure the mass, the temperature, and the specific heat. We then burn the fuel, which is the system. We will know the mass of the system and the temperature of the surrounding. We then determine the heat of the surrounding, which is the heat for water. And if we know the heat of the surrounding and then we have heat of the system, we can determine the Q of the system per gram fuel. So first we will have an empty can on the ring, and then we have some water inside the can. We measure the temperature of water. Next we have a fuel burner underneath the can. We will burn the fuel and the heat will transfer to the water in the can. And in this case we have a combustion reaction. The combustion of fuel is an exothermic process. Hydrocarbons are particularly good at releasing energy. Hydrocarbons is the compound that has hydrogen and carbon, and generally the gasoline is a form of hydrocarbons. Combustion involves a reaction of the fuel with oxygen to form carbon dioxide and water. For example, when we do a combustion of the gas, the cooking gas, which is propane. We produce carbon dioxide and water, and we release it. We release a lot of heat based on this chemical reaction. Generally, the combustion reactions are written in 1 mole of fuel. Sometimes we require the fractional coefficient for oxygen, or CO2 or water to balance the chemical equation. Let's do some sample calculation. How much heat is absorbed by 150 grams of water at 25.2 Celsius degree, whose temperature is raised to 38.3 Celsius degree? The specific heat of water is 4.184 joule per gram per Celsius. So in this case, we have a change in the temperature. We will apply the equation Q equal to mcat, where the mass, the specific heat capacity, and the change temperature are given from the problem. And we see that the Q of water equal to 8210 joule. And then the temperature change for the previous example was result of the combustion of 0.764 gram of fuel. What is the heat per gram of fuel? So we divide the heat by the mass of the fuel that we burnt, and we obtain 10,700 joule per gram. Since the fuel is releasing this heat, the sign is negative, and we can convert the unit to kilojoule per gram. For the safety, the lab goggles must be worn at all times. We use caution with the fuel lamps and tie your hair up. Make sure you watch the technique demonstration video before doing the lab.